In the last few years, researchers have extended methods such as GradCam, GradCam++, as well as the use of other statistics such as gradients and activations and so on and so forth to improve explanation methods. This is what we'll focus on in this lecture, which is on recent methods for explaining CNNs. So this is not just about explaining CNNs. These methods are developed more broadly for explaining any kind of a neural network. Let's see a few of them in this lecture. So if you recall our discussion on visualizing the data gradients, our overall approach was you forward pass your data X, any input image, to get the output through the neural network. Let's assume that the neural network is given by a function f. You get a y is equal to f of x, and y is the neural network's output corresponding to a particular class. It was a particular score, the way we saw it. Then we do a backprop to the image to get the gradient dou y by dou x, and using those gradients we visualized the image back in terms of the gradients by taking the maximum among the gradient across the channels, and we get such an attribution map. Recall, an attribution map is a map of how much each input attributes to the output. That's the reason it's called an attribution map. Let's now ask if this is sufficient to explain a deep neural network. Is this method sufficient? The answer is not always. So let's see a counter example where such an approach of using gradients can actually fail. Let's consider a scenario where we have two inputs, I1 and I2. They are fed into the next layer. So the bottom is the input, the top is the output. This neural network is presented this way. And these go into the next layer where, let's say, we have a ReLU activation function, and which now gives out an output h, which is given by max of 0, 1 minus I1 minus I2. Let's assume that those are the weights that the neural network has actually learned at that time. And let's also assume that the final output y is given by 1 minus h. This is one such neural network that may be learned when you train when you train a model. So if you visualized the gradients in this kind of a setting, you would notice that on the x-axis, if you had I1 plus I2, you would notice that h is max of 0, 1 minus I1 minus I2, which means when I1 plus I2 becomes greater than 1, h is always 0. Until then, it would be 1 minus I1 plus I2. So you see the graph of h will be this blue line here, where it is 1 minus I1 plus I2 until 1, and when I1 plus I2 exceeds 1, it becomes 0. On the other hand, the graph of y is given by 1 minus h, which means it increases as h decreases until 1, and when h becomes 0, y stays static at 1. This is evident from this kind of a construction of a neural network. This is fair. Now, why are we bringing up this example? What do we really want to see? We've already given a hint here. We're talking about something called a saturation problem. So what does that mean? We notice here that the gradient of h with respect to both I1 and I2 is 0 when I1 plus I2 is greater than 1. Which means as soon as the sum of the inputs exceeds 1, the gradient is going to become 0. So if the gradient is 0, the guided backprop or any other method that you use to visualize your data gradients in the first place will also be 0. That is one part of it. The second part is that the gradient of y with respect to h is negative. Clearly you can see that as h goes down, y goes up, which means the gradient of y with respect to h is negative. Remember that in guided backprop, we said that any negative gradient would also be made 0 when you backpropagate, which means even from 0 to 1, when I1 plus I2 goes from 0 to 1, even in that range, the gradient of y will be negative and we'll make it 0 due to the guided backprop approach. Which means the gradient now is always going to be 0 everywhere, which is not going to be useful at all. We call this the saturation problem. So how do you solve such a problem? So this problem was first pointed out by a work called Deep Lift in 2017. And what Deep Lift proposed to address this issue is, let's not use gradients, but let's use a variant of a gradient. Remember, a gradient by definition of first principles is you infinitesimally perturb an input and see what change it causes in the output. Now we are saying, let's not look at an infinitesimal change in the input or a perturbation in the input. Let's instead see if we had some reference input and our current input moves away from that reference input by a certain delta xi, one of the attributes. Xi is one of your input attributes. For an image, you could consider it to be one of your input pixels. So, and then we see what is the difference in output with respect to some reference output. So, if we moved from some reference input by a certain amount, how much does the output move from some reference output? So, it's no more an infinitesimal change. We keep a baseline for input and output and see if we move from the baseline by a certain amount, how much do we move from a baseline in the output. It's, as you can see, an extension of the idea of a gradient. And then you assign at contribution scores. These contribution scores are given by C sub delta xi delta t, such that the summation of all delta xi delta t's over all your attributes has to equal delta t, because that's the overall change in your output. So that's how the contributions of each input towards the change in the output is measured. You can see now that with this kind of an approach, the saturation problem that we saw on the earlier slide will go away, because no more will you be considering the difference between successive points on your x-axis, but you'll always be looking at it as a difference with respect to the reference, which you could keep as 0, and then y, even whether a point was at I1 plus I2 is equal to 1.1 or I1 plus I2 is equal to 1.2, it will still have a difference with respect to reference 0, and there will be a valid gradient, and your gradient will no more be 0. That's the way Deep Lift counters this saturation problem. So Deep Lift introduces a few different rules, in fact 3 different rules, but we'll talk about one of them here to be able to explain it. For more details, you can look at the paper. This rule is known as the rescale rule, and it broadly explains the idea behind the paper. So you start from an output layer L and you proceed backwards layer by layer, redistributing the difference of prediction score from baseline until input layer is reached. Let's explain that more clearly. Let's assume now that Zji is equal to Wji in the L plus 1th layer into the activation of the previous layer Xil. So Xil into Wji L plus 1 becomes Zji in the next layer. That's the notation we are using. Similarly, Zji dash is Wji L plus 1 into Xi dash, where Xi dash is the baseline input or the reference input that we talked about. So how do we use these? Let's now consider that Ri is the relevance of unit I and superscript L denotes the layer L. So the Ri in the last layer, capital L is the total number of layers. So Ri in the last layer would be given by yi of x minus yi of x dash, where x dash is the baseline reference input, and you're going to see what is the change in the output as you change the reference input. And that's going to be your relevance of unit I in your last layer. If there's no change, that's going to be 0 otherwise. For all previous layers, Ri of small l is given by summation over j's, which is all the neurons that you have that particular neuron is connected to in the next layer, zji minus zji dash by summation of all zji minus zji dash in that layer into rj l plus 1. Let's try to draw that out to make it a little clearer. So you have a particular layer with a few different neurons. You have a particular next layer with a few different neurons. We already know how to compute the relevances in the last layer. We are now taking one specific neuron I in the lth layer. Let's call this the layer L. So we take all the j's that are in the L plus 1th layer. So these are the j's that we have in the L plus 1th layer. And we see in the L plus 1th layer, so let's consider one particular j, its relevance would have already been computed. That would be given by rj L plus 1. And how much did it contribute to the relevance at RIL? That would be given by zji minus zji bar minus the summation of all zji minus zji bars in that particular layer. So that gives you an estimate of what is the relevance of node I at the lth layer. You keep backpropagating these relevances all the way back, and then you get an estimate of the relevance of each input at layer 1, which will be your input layer. Note here that the key difference, the process of backpropagation is very similar to what we did with gradients, but we are not computing gradients here. We are actually computing how much did the activation at any layer change by giving a baseline input instead of the current input. That difference is what we are measuring as the gradient, and the rest of the process stays very similar to what we did with backpropagation. So this is the idea of using deep lift to understand how each input neuron attributes to every output neuron yi in this particular case. Another popular method rather, is known as integrated gradients, very popularly used today. And integrated gradients is motivated by an observation similar to deep lift, which is shown here. So if you have a given image, which is an image of a fireboat, and if you only used the vanilla data gradients to see where the fireboat is, you get a set of gradients such as what you see on the right side. This kind of a structure in the gradients is predominantly because of a saturation problem that you will see on the next slide. So what do? What integrated gradients does is to avoid this problem of saturated gradients by accumulating gradients at different pixel intensities of the given image. Let's see this in more detail. So here are the same set of gradients, but now each image in this set of tiles here is the input image, however, with a reduced intensity at each pixel by a particular scale. So you notice here that there's an alpha of 0.02, alpha of 0.04, alpha of 0.06, alpha of 0.08, so on and so forth. All of this says that this first set of gradients were obtained by taking the given image and scaling down its intensity by to the level of 0.02. So it becomes imagine an image that's an interpolation between a black image and the current given image, but you weight the black image to a level of 98% and the current image to a level of 2%. That's what alpha is equal to 0.02 will give you. Similarly, you can do alpha is equal to 0.04, alpha is equal to 0.06, so on and so forth, and you get a different set of images. And for each input image, you can compute your data gradient. And now you see that you start seeing more structure, more clearer structure in the data gradients. Why is this clearer structure? Because this is a fireboat, you would ideally want to localize the boat as well as all of these water streams, because that's part of the nature of the boat itself. And that's what you see on all of these gradients here. But as you go closer and closer to the full image, you see that perhaps the gradients are close to each other, and hence the method, if you use any data gradient, it thinks that all of the pixels have about the same gradient, and then you end up getting a cluster of gradients like this, which really don't isolate out the key pixels. Let's see this also mathematically to make this a bit clearer. And mathematically, this is achieved using what is known as a path integral, and that's the reason it's called integrated gradients. Let's try to see how that's defined. Ig, or the integrated gradient along ith dimension for input x and baseline x prime, which we just took as a black image when I gave the example a minute ago, is given by igi of x is equal to xi minus xi prime. When you have xi prime to be a black image, that will always be 0. So this will just be xi itself. And you integrate alpha from 0 to 1, and then you do dou f, where f is the neural network, x prime plus alpha into x minus x prime by dou xi into dou alpha. What is this partial derivative? It's taking x prime plus alpha into x minus x prime. So you have a black image and you keep adding little and little of the given image to the black image. And now you take the output of the neural network f as you forward propagate that constructed image between a black image and a given image and differentiate and that with respect to the input. Now you compute the data gradient of this interpolated image, and you find all such interpolated images as you move alpha from 0 to 1 and then integrate all of them to be able to get an integrated data gradient. They show that this kind of an approach can lead to more robust attributions. But in practice, it's not possible to integrate over all possible alpha values. So we come up with an approximation where we take a set of alpha values. We define a set of intervals between 0 and 1, and we keep stepping on from each of those intervals. So summation goes from k is equal to 1 to m, and then you have a k by m. So you take it at 1 by m, 2 by m, 3 by m, 4 by m, so on till m by m 1. So you keep taking those steps of your input image added to a baseline image or a black image, and then you compute your data gradient and average out all your data gradients, and that becomes your integrated gradient. Now you have an IG attribution map which focuses on the fireboat as well as those streams of water, which is far more convincing than what we saw initially with the vanilla gradients. Another approach that was proposed is known as smooth grad, which uses a very similar idea as integrated gradient, but a more heuristic and a simpler approach. It says, let's add pixel-wise Gaussian noise to many copies of the image and average the resulting gradients. Why do I have to do the path integral to go from, say, a black image to the given image? Instead, let me take a given image, I'll just distort it in several ways using by adding Gaussian noise, and now I'll compute a data gradient for each of those images when I forward propagate that image through a model, and I average all of those gradients, and I now get a new data gradient which I'm going to use as my final attribution map. An interesting observation that you can notice here is that this method talks about removing noise from the saliency map by adding noise to the input, which is an interesting approach, and it actually works reasonably well. In fact, there are many other methods now which have added a smooth variant to their approach. For example, there's also a smooth IG approach which takes the integrated gradient and takes a smooth version of it by adding Gaussian noise to different inputs and then averaging the data gradients. So here you see an example of a result. You have the original image. You can see that the vanilla gradients are spread out across the image. You do see an outline of the structure, but otherwise the gradients are spread out across the image. But by doing smooth grad, you get a fairly robust attribution map of the gradients which corresponds to the object. A more recent variant of integrated gradient is known as XRAI. It was published in ICCB of 2019, where the idea is to take integrated gradients, but in the context of computer vision, to treat it in terms of segments rather than pixels. So far, we talked about attribution maps of every pixel towards a particular output class. But doing it at the level of every pixel can become tedious in an image. Instead, can we reason at the level of segments in an image is what XRAI tries to do. Fairly practical approach. What it does is you first get the attribution map given by IG. So that's the first step that you need to do. I should point out here again that all these methods that we are covering this entire week, including this lecture, the previous lecture, in all of their cases, we already have a trained model. We are now talking about after a trained model, what are the different things we can do. These are not methods that affect the training of a neural network. That part of it we already did. We are now trying to see, given a trained network, how can you explain its behavior? Let's come back to XRAI. So you get an attribution map given by IG, and then you over segment the image, which means you get a lot of segments in the image. And now you start with an empty mask, which means there's no mask to start with. And then you'd add a region which has the highest sum of attributions in a given segment. So you have a number of segments in an image. You pick the segment which has the highest attribution among all its pixels in that segment. And that is the first segment that you're going to add as corresponding to a particular class. Remember, these attributions that you have, that you add into a segment, are attributions with respect to a particular output or a particular class. Let's see a couple of examples here. So here you see an original image. So integrated gradients does give you a region around those hot air balloons. You also get a few other places some gradient. But by doing XRAI, you get a fairly neater presentation of which aspects or which regions of the image were responsible for these objects to be called hot air balloons. Let's see another example. So here is an original image, and as you keep adding 3% of segments, 10% of segments, you see that more and more objects keep getting added. The way it happens is you start with XRAI segments. So this is the over segmented image that we are talking about at the bottom. So you now try to find out which of these segments has highest attribution pixels, highest sum of attributions of pixels corresponding to the object bird. And you take that region, and if you take the top 3% of such segments, you would get this region. If you take the top 10% of such segments across all your segments, you would get these two regions, and these would be the corresponding XRAI heat maps. So it's a way of extending integrated gradients to reasoning at the level of segments instead of pixels.